numbers. And so I actually checked it before, but it works on the plan, like a day before. But actually during the presentation, I realized that like the third slide was missing, or something like that, and then they started to come in a random order. And it turned out that, it took me some time, but like after the presentation ended, I realized that what actually had happened was that MacBook decided to play them in the last modified order, rather than by file names.
That's so strange. I hate MacBooks.
Okay, let's continue so that our visitors from the world wouldn't get bored. Okay. So here I can change the angular speed of the rotation. Now it's -3. If I increase it, actually decrease it, it's gonna go faster, right? I can stop it. So let's see if it works. If it stops,
include the
if it does,
limit.
you're gonna see. So now it's stopped, right? Now it doesn't rotate. Now it's gonna rotate to the left. Yeah. And so that's the second one. Okay, now watch this ball in this frame. So what happens is it goes between this red guy and this red guy. You may view it as there was like a tower and here a tower and a rope between these towers, and there's some object moving along the rope with a uniform speed. So it's completely disconnected with the platform. And if the platform rotates, it just moves above the platform. Now watch this in this frame. This rope is like that, now it's like that, now it's like that, now it's like that. So it's actually nothing special. But if I remove my drumstick, you see how it deflects. It actually gets deflected so that it's moving together with the guys. So it's deflected. Okay. Now I'm going to show you how my program works, more or less. Okay, so the main loop, blah blah blah. Okay, what matters is this. So here I can define my objects. I have matrix of objects. So it's got like 6 elements. So element 0 is the existence. 1, if it's 1, I can define its motion in the lap frame. If it's 2, I can define its motion in the rotating frame. I can block it by setting it to 3. So if I block it, it's not displayed. Then I can enter x and y coordinates of the initial x and y coordinates, either in the rotating or in the lap frame. And then I can specify it's all circles, because I'm a physicist, I can only think of circles. So it's all circles, and this is the radius. And then also I can specify the color. So these 4 and these 4 are the guys. One of them are sitting on a table, and they are green, and other guys are sitting outside and they are red. And then there are other objects. So this thing was the yellow ball, right? It started somewhere here, and then down. Yeah. And when the defining procedure ends, it goes here. So what I want to show you is that, so this is the loop, the time goes, right, from 0 to 100, and each time...
I like the T plus the T.
And each time it goes to this function, motion, which defines the motion of this object. So for example, this is the motion of the ball that you will see in this yellow thing. It just, and if it's 2, that means that the y coordinate in the lap frame. So it moves. So it's each time it enters this function, it's incremented by 500, which is its velocity times dt. And for example, we have a more interesting example for later time, which is a harmonic oscillator, an apprentice. So this is the displacement, so that it was displayed in the middle of the window, and that's just 70 amplitude times sine of omega. Okay, that's what I wanted to show you. Oh, and by the way, so, and then it jumps to this function rotate, and all it does, it just calculates the coordinates in the other frame by applying the rotation matrix. See, cosine sine minus sine cosine, and here's the inverse. So that's cosine minus sine cosine. That's what I do. I don't enter any forces. I only rotate that. So that's just pure geometry. Okay. Is that important? No, it's not. Okay, so now you can appreciate my programming again. So I defined this ball in the lab frame, and this is just the rotated version. Okay. So now I can show you. So first thing I show you. Okay, I've adapted you, and I've do that. Okay, so now I'm gonna show you what happens if you place a cannon at the origin, at the middle of the platform, and if you shoot a ball out of the cannon. So I have to block this ball, shouldn't I? Wait. Yes, I did. No, I don't. Yes, I did. And this is the cannon.
So is the cannon on the platform? Is the cannon taking?
Yeah, it doesn't matter actually, because it's what matters is the initial speed, initial velocity of the ball. But then it just moves with that velocity, and it doesn't have contact with the platform, right? So that's how it looks like. Are you ready? Yes. Oh. Okay, something doesn't work. Sorry. Probably I didn't. Oh yeah, because that's the motion of that ball. Okay. Yeah. So it just shoots this yellow ball out. But what you see in the rotating frame is that this ball is deflected to the left. So we can view it as like this direction. This direction is like downstream, and this is upstream. So okay, maybe I should show you right away another example, which would be like 8 cannons at the origin. Okay, and that's. I should block this, and these are the 8 cannons. So now we're gonna see the same thing, but there will be 8 balls shot out in 8 directions. Yeah, okay. But 2 of them don't go quick enough. Actually 4 of them. Wait, because I know, I should fix that. Has anybody got a calculator? No. That's 250. Oh, because I didn't fix that. Yeah, okay. So that's easy, right? They just move away from the origin. But what you see there, well, what you see is that just this pattern rotates. And if you think of forces, then you see that these balls, I mean, all of them get deflected in counterclockwise direction. Like this was upstream and this was downstream, so that's what you see. What would happen if I change the angular speed to 3?
Goes the other way.
Yeah, because then that would be downstream and that would be upstream. Yeah, that's easy. Oops. So there it is. So it actually, if you think of comparing these two, it gets deflected in the opposite direction of the rotation as viewed from the lab frame. Yeah, so coming back to one cannon at the origin, this explains that thing with daddy on the merry-go-round. Because you can think that, oh yeah, this is the daddy. I was going clockwise, so I should fix that, sorry. So now, this is the merry-go-round, this is the daddy, and this is the cannon. I mean the ball. And this is the daddy on the left. But if it was going, and you can see it here as well. This is the ball, that's what you would see. And the ball gets deflected. I forgot what I wanted to say. Oh, and if it was moving, rotating the other way around, of course, it misses the daddy from the left, from the right. And that's what you see here as well. Good. And also it explains the airplane, right? Going from London to Paris, probably.
Yeah.
It's just the same thing. And at least when it goes from London to Paris, because when it goes from Paris to London, something strange happens. And then, oh yeah, that's a good one, but I think it's
From Paris to London, you would rather take the Euro train instead of flying.
Well, I have an idea of what might happen with that, because I understand that currently we have that paradox with going the other way. Perhaps it has things to do with how the velocity of Earth's surface differs depending on the latitude. So you actually, when you are starting, you already are moving with the velocity of the Earth. So what's more towards the north is moving in the same direction but slower. So what's basically north seems to move towards east.
Actually, I didn't catch it.
Basically, when you start, you are already moving with the velocity of Earth. However, the point that is more towards the north moves slower to the east. Therefore, it appears that north is going to the west. And
the east, because I mean the plane. So you're saying that the plane would move with higher speed than the point at north. So when it goes to the north, it's got bigger speed to the right than the point on the ground.
yes, the plane has bigger speed
So it
to
would be
the east. So the point on Earth's surface, on the north, seems to be moving westwards.
Okay, next thing that I prepared may not work because of this changing of size of the window. So maybe, I don't know if you want to see it.
What was
Maybe you don't.
Is it the pendulum? I mean, pendulum sounds good. But
Pendulum, but that's later.
okay.
Now we're gonna have 3 balls, actually 2 balls, and we're gonna see how one doesn't go in a loop, and the other one does. And then, so I should draw it. So there will be one ball, which is going to be deflected like that, and another ball, which is slightly in that direction, it's going to do this. So that means that in between it's possible to shoot out a ball which will do this, and stop here, and go like that. And then I would ask you to calculate where this ball should start, and then I will put it in, and you would see that. Sounds fun?
But where do you shoot the ball from?
Okay, so let's see.
What do you mean? Are you on the circle? Or?
No, it doesn't matter. What matters is the initial speed.
But you're shooting it from the middle, like with your camera.
No, from the side.
This
time. Now what should I block? It's already blocked. No, it's not. Oh yeah, because there are 8 balls. So actually it's